Hello, everyone. Uh, my name is Ru Jieyang from Zhejiang Agri and Forest University. It's a great honor to come here to give the oral presentation in the 5th International Conference on Desalination using memory technology. The title of my presentation is Controllable Current-Linked Side-Zero Graphene Oxide Memories for Improved Sodium Chloride Rejection. This is the outline of my presentation. The first part is the introduction. Water scarcity is a key global concern, and desalination using memory technology from seawater can largely increase clean water supply. During its sustainability, environment friendliness, and low cost. Recent years, graphene oxide geo memories have provided greater potential in memory separation due to its some advantages such as ultra-thin, high flux, and energy efficient. However, the gel memory suffer from the swelling effect in water and resulting the worst rejection performance for desalination. To solve this limit, some effective strategies have been developed. For example, in our previous work, the cation type controlled interline spacing of gel-based memories was with atom prison was proposed, and this method stronger cation pair interaction between eyes and high conjected system. Based on this work, we have further prepared the passive eyes modified reduced graphene oxide memories, and these memories show the
瑞杰，你的网络好像有点问题啊 ，Sorry， you have trouble with your internet. 如杰，you have a problem with your internet. Can you stop and restart? Sorry, we have some trouble with the internet, and we will hold for a few seconds to let him log in. Sorry for his trouble. Perhaps it's best that if you can record your presentation and just broadcast it. 瑞杰, can you restart? Your network is not good enough.
Sorry, the internet is on. It's okay.
Perhaps you can switch off your video. You can save some data. Go ahead, please. Speed up.
Thank you.
Switch off your video. Yeah.
Thank you. We have further prepared the potassium as modified reduced graphene oxide memories, and these memories show the ultra high water permeance up to 86.1 mmHg bar and meaning the excellent rejection up to 99.6% for multivalent ions, which exceeded the corresponding values of state-of-art nanofiltration memories for multivalent metal ion rejection. However, these memories suffer from insufficient rejection, especially for small size salts such as monovalent ions. More importantly, increasing selectivity is crucial required for design of novel destination memories. So we hope further increase the rejection of the monovalent ions. Recently, the cross-linking, molecular cross-linking is also a promising method for prevent the gel swelling and control the interlaced spacing. So the set zero with small molecular skeleton and two reactively terminal group was chosen as a development-friendly cross-linker, and the alkali environment potassium hydroxide solution plays a key role in effectively facilitating the set zero cross-linking reaction process, and the potassium ions enter the set zero graphene oxide membranes to effectively fix and control the interlaced spacing at the same time. So the cross-linked set zero graphene oxide membranes treated by potassium hydroxide solution are expected to effectively reject sodium chloride solution in a press-driven filtration process. And the next part is the methods of memory preparation. Firstly, the graphene oxide solution was prepared by improved human methods, and the set zero was dissolved in the solution and was placed in a water box for 45 degrees centigrade and half an hour, and the obtained solution was then diluted and run through a MCE substrate under the pressure of 1 bar to realize the assembly, and the memory was then placed on an oven for an hour to obtain the set zero graphene oxide memories. And afterwards, it was then soaked in potassium hydroxide solution to obtain set zero graphene oxide potassium hydroxide memories. Next is some results and discussion. First, the memory morphology was characterized by SEM, and from the cross-section of the SEM images, we can see their memory thickness are all about 100 nanometers. And from the surface morphology, the memories show the smooth and visually defect-free surface, which is crucial for effective desalination process. And then we further use the EDS mounting to confirm the homogeneous set zero molecular incorporation for set zero graphene oxide memories, and the locations potassium ions were homogeneously dispersed within the set zero graphene oxide potassium hydroxide memories. After the observation of memory morphology, the Raman and FTIR was used to characterize its chemical properties, and the results show that there is a partial consumption of geo-corresponding oxygen group when cross-linking reaction between set zero and graphene oxide, and a new bond carbon-nitrogen bond was formed, and the cross-linking degree of Side-zero graphene oxide potassium hydroxide memories was enhanced, and then the STS was further used to confirm its chemical properties. And from the analysis of SPS elemental composition and the percentages of oxygen-containing group, we can see that the amine group in side-zero reacted with carboxy and iboxy group on graphene oxide to form covalent bond, carbon-nitrogen bond, and the cross-linking degree of side-zero graphene oxide potassium hydroxide memory was enhanced, which is consistent with the Raman and FTIR results. Additionally, the salt sieving ability is an essential indicator for evaluating nanofiltration memories. So the filtration memories of these memories was tested by sodium chloride and sodium sulfate solution with a concentration of 15 ppm under the pressure of 5 bars. And the results show that the rejection of the side-zero graphene oxide potassium hydroxide memories raised up to 93.1% for sodium chloride solution in press-driven filtration process. Additionally, to further evaluate the press-resistant capacities of side-zero graphene oxide potassium hydroxide memories, it was subjected to different applied pressures, and the pressure increased from 3 to 9 bars. The water permits increased gradually, and the rejection was all remain nearly 93%, which is crucial for industrial application. On the other hand, the side-zero graphene oxide potassium hydroxide memories still have excellent separation performance under the high pressure up to 9 bars, indicating that the memory possesses a robust microstructure and could understand a high pressure up to 9 bars. Thus, mechanical stability and stability is also crucial for industrial application. And then we compare the separation performance of the side-zero graphene oxide potassium hydroxide memory with other reported natural filtration performance. And the table shows that the rejection performance of side-zero graphene oxide potassium hydroxide memories exceeds the performance of most commercial nanofiltration memories and the GOB destination memories reported in other literature. And then we further performed the UV absorption spectra to understanding the underlying physical mechanism. The UV spectra show that the extent of potassium ion pi interaction in the side-zero graphene oxide potassium hydroxide memories, which could further lead to the improved rejection of side-zero graphene oxide potassium hydroxide memories. Then mechanistic insight is proposed here to understand the enhanced rejection of this process. The alkaline environment potassium hydroxide solution effectively facilitating the side-zero covalent cross-linking reaction process, and potassium ions can enter the side-zero graphene oxide memories to effectively fix and control the interlace spacing by the potassium ions pi interaction, resulting in the improved rejection of side-zero graphene oxide potassium hydroxide memories. From the above discussion, we can draw some conclusions. First, we demonstrated that the current-linked side-zero graphene oxide treated by potassium hydroxide solution achieve high sodium chloride rejections under high external pressure with excited rejection performance of most commercial nanofiltration memories and graphene oxide-based destination memories reported in other nature. The improved rejection of the side-zero graphene oxide potassium hydroxide memories was attributed to the enhanced cross-linking degree under the alkali environment. In addition, the cation-pi interactions between potassium ions and CO sheet with fixed and controlled the interlace spacing also could increase the memory rejection and stability. Finally, I would like to thank the funds supported for this research. Lastly, I would like to thank my supervisors, Professor Liang Chen and Dr. Shansha Liang. That's all my presentation. Thank you for your attention.
Thank you, Rujie. Can you switch on your video? So I think we are really lag in the timing because you talk about 15 minutes. You are supposed to give 12 minutes so we can have time for questions. While we are waiting for the questions, I have one remark on the membrane you just talked about. What is the stability of your membrane when you use strong acid to treat your membrane, to clean the membrane, or strong base to treat your membrane?
The memory, the graphene oxide, the side-zero graphene oxide potassium hydroxide memories was tested under the pressure of 9 bar.
No, my question is not about pressure. My question is about how strong your membrane is in a strong acid or a strong base. For example, in pH 1, pH 14, have you tested this the stability of your membrane in such extreme acid and base conditions?
In this study, the memory was treated by potassium hydroxide solution. It's alkali environment. The acid environment.
Okay. What is the pH of your treatment solution?
The effect of pH on the memory stability is not studied now. We hope to further study the different pH for example, pH value 1, pH value pH equals 10.
All right. Thank you. Thank you for your nice talk. We are moving to the next speaker. Now our next speaker is Ke-Chen Guan from Kobe University. His talk is about multi-layered graphene oxide membrane with confined nanochannels for ion exclusion. Rujie, can you switch off? Because the next speaker will show their slides.
Okay, can you see my slides?
Yes, clear. Go ahead, please.
Okay. Hi, everyone. My name is Ke-Chen Guan from Professor Matsuyama's research group at Kobe University. And it's my great honor having this opportunity to share our recent research work entitled Multi-Layered Graphene Oxide Membranes with Confined Nanochannels for Ion Exclusion. And we all know that the world is facing water scarcity, especially in recent years, and membrane technology provides a great solution to alleviate this issue. And for membrane technology, different membrane processes can be used for the separation of different types of pollutants. Here we focused on the separation of ions. So currently the currently the polyimide membranes works very well for the desalination process, including reverse osmosis and nanofiltration, because the inhomogeneous pore structures and abundant pore density of this polyimide membrane can provide high water transport. But in contrast, the recently developed the two-dimensional material membranes, it has a well-defined channel, which is quite different from the polymeric membranes. And this interlayer channel formed by the stacking of two-dimensional nanosheets can provide some building block-like properties for the assembling of this structure in a feasible way. So we can modify the local structure of the membrane very easily. For example, we can control the channel size by introducing some reactive molecules inside the nanochannel, and we can even fabricate some smart channels which has response property to external conditions. So actually this nanochannel is very promising for a wide range of applications. So here, the graphene oxide is one of the most widely used two-dimensional nanosheets, but the biggest challenge for the GO graphene oxide membranes is the instability in water, especially when the interlayer channel is on the water. The interlayer channel size can be expanded to several nanometers, which is obviously not suitable for the separation of sub-nanometer sized ions. So in order to fabricate this stacked multi-layered graphene oxide membrane for the successful rejection of salt ions, we should limit the expanding of the interlayer spacing. So in our work, we fabricated the reduced graphene oxide for trying to improve the water stability of the graphene oxide membranes. And also after the reduction, the nanochannel confinement can be increased due to the enhanced stacking between neighboring nanosheets. And also, more importantly, the charge effect of original graphene oxide membrane can be retained because not all of the oxygen groups have been reduced during this reduction process. And then we tested the salt permeation through this RGO membrane, and we found mainly the salt permeation is dominated by the charge effect. For example, for A2B type salts with divalent anions, which is also the co-ion of the membrane, it shows the highest water salt selectivity. But for the AB2 type with divalent cations, which is also the counter-ion of the membrane, it shows the lowest selectivity. So we proposed the mechanism of nanochannel confined charge repulsion of ions for this type of membrane. And considering the transport of hydrated ions through the membrane, when the hydrated ion enters the pore entrance of the nanochannel, if the nanochannel size is smaller than the size of hydrated ion, this ion should dehydrate to remove some water shells to fit inside. So this will lead to the dehydration-based energy barrier. And when the ion is transporting inside the nanochannel, the functional groups from the pore wall of the nanochannel will establish some interactions with the ion to retard the ion transport. So this will lead to the interaction-based energy barrier. So if we decorating the pore wall with some favorable molecules with charged groups, we can obtain possibly higher ion rejection. So firstly, we tried to study the nanochannel confinement effect, so which is corresponded to the dehydration-based energy barrier. We fabricated different RGO membranes with different reduction degrees. We can see from the XRD spectral, with the increase of the reduction degree, the peak shifted to the right side, which indicates the narrowing of the interlayer spacing. Of course, this narrowing of interlayer spacing leads to the decreased water flux, but the salt rejection was improved a lot, especially for the sodium chloride. We can see the rejection ratio was improved from around 10% to 90%. And next, we studied the charge effect of the nanochannel, which is corresponded to the interaction-based energy barrier. We selected two types of porphyrin molecules with different charged groups to be intercalated inside the nanochannel. And for both type of modified RGO membranes, we found that the salt rejection was slightly increased with the intercalation of the TCPP molecule with carboxyl groups and the TAPP molecule with amine groups for different types of salts. But actually the increase of the rejection is not so significant, possibly because the confinement effect of the original RGO membrane is contributed much more for this rejection improvement. So maybe it was not that obvious for the Chat effect studied here. And anyway, we successfully fabricated the ion exclusion nanochannels by a two-step strategy. The first step is to limit the nano confinement of the nanochannel, and the second step is to introduce some charged groups inside the nanochannel. So next, we want to simplify this procedure to a one-step reaction, which can introduce both channel confinement and charged groups at the same time. We selected the tannic acid as the modification agent because it has many phenol groups which have activity to reduce the oxygen groups of graphene oxide, and also the unreacted phenol groups can act as charged groups in the finally resulted membranes. So we evidenced the successful synthesis of chemically converted graphene oxide. We can see from the optical images here, and also evidenced by the UV visual spectrum. So we also prepared another sample with simple mixing with tannic acid and the graphene oxide. But we can see from the IR spectrum here, if we just simply mix tannic acid with graphene oxide, the oxygen group's intensity cannot be decreased. Actually, it was increased compared to the original graphene oxide because the introduction of tannic acid. But for the reacted mixture CCG, which is labeled as TARGO here, the intensity was decreased, which means was also evidenced the successful reaction. And we started the nanochannel properties with comparing to the original graphene oxide membrane. So the first point is confinement. The graphene oxide interlayer is not stable underwater. When the sample is wetted by water, the peak shifted to the right side or left side, which indicates expanded interlayer spacing. But for the modified RGO membranes, the peak position was kept similar in a similar position. More obviously, from the water permeation test, we can see although the initial flux of original graphene oxide membrane is very high, but after some time, the flux sharply decreased, maybe to around less than 1% of its original flux, which means this interlayer spacing of original graphene oxide is not stable, and will suffer more from the compaction effect during the filtration process. But for the modified geomembranes here, the water flux is stable through this process. And the other point is the charge of the nanochannel. We studied the data potential, surface data potential of the two types of membranes. Actually, the tannic acid reduced graphene oxide shows the similar data potential compared to original graphene oxide. Normally, the RGO membrane should have less negative charge because the oxygen groups was reduced, some of them. But because of the introduction of tannic acid, so we can keep a similar charge density here, which resulted in a similar data potential. And of course, we tested the different salt rejections for both membranes. Both membranes showed the permeation was controlled by the charge effect, but with the introduction of confinement effect here, we can see we can achieve, for example, two times rejection of original graphene oxide for sodium chloride rejection. And we also explored the membrane stability under different conditions. We exposed the membrane in acid or alkali conditions and found that the nanochannel stability, nanochannel is stable in both conditions with same XRD spectral shown here, the geo peak shown here. And we also tested the water permeation, water filtration process. We treated the membrane with acid and alkali during this process, and the membrane kept a similar performance during this situation, including the permeation flux and the salt rejection. And we also tested the effect of operation temperature for this membrane. We increased the temperature to 70 degrees C and then decreased. The membrane kept stable in this process with similar rejection with well corresponded water flux. And we calculated the activation energy of water transporting through this type of membrane and found that this value is comparable to the polyamide membranes, which is also indicating the our membrane is very permeable to water. So to conclude, for two cases I mentioned here for the ion transport in graphene oxide membranes, the charge effect is the dominating factor in controlling the ion transport. And the channel confinement is very, very important and is very effective to maximize the charge effect to retard the ion transport. And we can also obtain some favorable nanosheet building blocks by using some suitable reactive agents which can simplify the modification procedure. So thanks for listening, and I'm glad to answer any question you may have.
Thank you for your nice talk. Very nice work.
Thank you.
We are going to the Q&A session. Because typing will take some time, you understand. Because a lot of questions also from my side. Perhaps I can initiate the discussion a bit. You have talked about the separation of controlled confinement. So the confinement, where does the confinement came from? From the reduced GO, or from the added chemicals in between the GO layers? Can you elaborate a bit?
Okay. The confinement is from the stacking between neighboring nanosheets. After reduction, some of the oxygen groups can be removed, so that the pi-pi interaction between two nanosheets can be enhanced. And also the removal of oxygen groups can narrow the interlayer spacing, which means the stacking of the neighboring nanosheets can be closer and a stronger interaction. So this will result in a more confined channel. Okay. And will not allow the excessive intercalation of water molecules.
Yeah. There is a question from the audience. Membrane performance depends on the charge action and the d-spacing.
Yes.
Ions will hydrate again between layers.
Yes.
Will affect the membrane performance?
Yes, actually, we found even if we reduce the membrane, graphene oxide membrane, the channel still can be wetted by water molecules. Because we can see from here, although the confinement is enhanced, but it still allows the transport of some larger sized ions, such as magnesium ions, calcium ions. They still can pass through the membrane, which is quite different from the polyamide case. Because for polyamide membranes, the larger sized ions can be rejected first, but the rejection for sodium chloride is lower compared to this one. So different mechanism. I think the channel still can be hydrated underwater, even if we reduce the membrane.
Does this mean, just following the question, does this mean the spacing you design in your membrane is quite large? So it's slightly larger than the hydration radius of magnesium ions?
Yes, I think the mechanism, the hydrated magnesium ions can dehydrate. If the size is too large, it can dehydrate to remove some water shells to enter this pore size. And I think the size is not enough to establish steric hindrance towards hydrated ions. Only can like to enhance the energy barrier for the ion transport.
Okay. Thank you. It's time to move on to next session. Just last question. Are you PhD student or postdoc?
I'm postdoc in confinement.
Okay. Thank you. Thank you very much.
Thank you,
We are going
Professor.
to move to
Thank
next speaker. Thank you.
Thank you.
And now we move to our last talk for the first session. Please invite Liang Ying. His talk is about 3D electrohydrodynamic printing of chlorine-resistant desalination membrane for boron removal.
Thank you, Professor.
Yeah,
right.
Please, go ahead.
Okay, good day to everyone. So I'm Liang Ying, a PhD candidate from National University of Singapore under Professor Sam Lee's research group. So it's an honor for me to have the opportunity to share part of my PhD research on 3D electrohydrodynamic spray printing of chlorine-resistant desalination membrane for boron removal. So in 2018, Chowdhury and his team published in Science on their breakthrough in introducing a novel polyamide membrane fabrication method through electrospray printing, which can lead to much thinner and smoother membranes that are favorable for high desalination performance and water permeance. So in our research, we replicate an electrospray printing setup and process and demonstrate.
Hold on, please. You didn't show your slides yet.
Oh.
We are seeing you talking.
Oh, okay.
Although we like your face, but we also want to hear your work. Sorry.
Can you see my slide now?
That's perfect. Go
okay,
ahead.
Okay, yeah. So, like I mentioned, in our research, we replicate an electrospray printing setup and demonstrate the high dispersibility of the nanofillers for the purpose of chlorine resistance and boron removal in polyamide desalination membrane. So the high tendency of fouling and low chlorine resistance from cleaning the polyamide membranes are two huge bottlenecks to be overcome. So moreover, the presence of boron at high concentration in seawater is detrimental to the human health. Therefore, we seek to control the surface morphology using electrospray technique to improve the surface roughness, as well as that translates to the membrane fouling problem. While chlorine resistance and boron removal could be achieved with two novel nanofillers, namely the protonated montmorillonite nanoclay, abbreviated as MMTH+, and aminopolyol cellulose nanocrystal, APCNC. So briefly, the MMT was activated with strong sulfuric acid for cation exchange with the calcium and magnesium present in the pristine MMT. So this exfoliation and destruction of the nanoclay interlayers is then evidenced in the powder XRD, where a larger interlaminar spacing with slight shift towards the left of the indicative peak shows otherwise. So the total sodium exchange capacity was determined to be 0.7 milliequivalents per gram, and that is 13 times higher than the pristine MMT itself. So looking at the BET results, it has shown that the exfoliated and activated MMTH+ is highly porous to facilitate the exchange with the sodium ions in the feedwater. So on the other hand, the synthesis of APCNC went through a series of oxidation, carbodiimide cross-linking with the polyethylene imine, and then finally grafting with glyconic acid. So this extensive presence of the amine as well as hydroxyl group will eventually support their complexation with the different boron species in the feedwater. So an additive approach is presented that uses electrospray printing to deposit monomers directly onto the UF substrate, where they react to form a polyamide layer. So using high voltage, the two precursors are finally sprayed onto the substrate and polymerized on contact. So this small droplet size coupled with the low monomer concentrations that we optimize result in the polyamide film that are smoother and thinner. So by comparing the surface topography images of the polyamide, which is abbreviated as PA, as well as the polyamide with 0.3% of the MMTH+, which is abbreviated as PAM, we can observe that the nanoclay was well dispersed within the polymeric layer. And this indicates that there's a wide coverage with the addition of this particular nanofiller to protect the polyamide membrane during the cleaning process with sodium hypochlorite. Then the membrane loaded with 0.2% APCNC afterwards reveal a layer of small and highly crystalline structures highlighted in purple above the polyamide layer. So the increase in APCNC actually influences the thickness, as we can observe over here, of the polyamide layer itself. And hence, one possible explanation could be that there could be an agglomeration of the APCNC on the polymer area. And this can be evidenced from the AFM phase images as well. So basically, an excessive concentration of APCNC results in an increase of surface roughness and would eventually translate to a fouling tendency also. So PAM 0.2 APCNC, which denotes the loading of 0.3% MMTH+ and 0.2% APCNC, was able to achieve the lowest salt permeability coefficient, which is supported by its high salt rejection efficiency of 87% and 85% for sodium and sulfate ions, respectively, with the feed containing 30,000 ppm of sodium sulfate. So moreover, PAM 0.2 APCNC has the highest water to salt permeability coefficients compared to the rest, and this could again attributed to the excellent dispersity of the nanofillers on the membrane thin film surface with high cross-linking density. Unfortunately, we can observe breakage of the mechanically weak polyamide thin film with higher APCNC loading at 0.5% and 1% loading. That results in poorer salt rejection efficiency over here, and also attributed to lower water to salt coefficient permeability ratio. So we can actually understand from this case that there is also a limitation of the electrospray fabrication technique, whereby there is a loading limit of the nanofillers that we could include during the membrane fabrication before they start agglomerating. So in order to evaluate the effectiveness of the MMTH+ to provide the protection of the polyamide membrane, so these membranes were exposed to 1,500 ppm of sodium hypochlorite cleaning, and we can observe that the membrane incorporated with MMTH+ observe a much less significant drop in the ions rejection. And needless to say, the increase in the flux and lower rejection rate indicated some form of degradation to the structural integrity of the membranes. So we have conducted elemental composition analysis on the treated membrane surfaces, which reveals that there's a high possibility of amide linkage cleavage due to the hydrolysis of the polyamide. And the high oxygen to nitrogen ratio indicated the presence of more carboxylic group arising from the hydrolysis. So furthermore, the higher intensity of the CCl peak may indicate that there's a higher rate of N-chlorination that can result in irreversible auto ring rearrangement. So if we look at the chlorine treated PA membrane incorporated with MMTH+, there is less extensive chlorination that is observed, and hence that is why we can observe the less effect of the chlorine attack on the desalination performance. So finally, we simulated the boron removal experiment with seawater pH, wherein boric acid is the predominant species. So membrane loaded with 0.2% APCNC once again obtained the highest boron removal efficiency of 77%. And this complexation capabilities of APCNC was also described using the molecular simulation, where electrostatic interactions between the nanofillers APCNC and boric acid is the most significant. So also the change in the potential energy also further supports the spontaneity of the interactions between APCNC and boric acid. Hence, we can also safely say that this is a viable nanomaterials effective for boron removal. And to end off, we have presented the benefits of electrospray fabricated techniques to promote low fouling tendency with prolonged cycle life. Chlorine cleaning with polyamide membrane can also be possible with the incorporation of protonated MMT as the protective layer. And finally, APCNC offers a cost-effective and efficient alternative to removing boron in a single cycle desalination. And this also translates to promising applications to produce safe drinkable water at lower cost in near future. And finally, we would like to acknowledge the funding and facility supports from our collaborator and research centers. And with that, thank you so much for your kind attention.
Thank you, Yang Ying.
Thank you so much.
Interesting talk using spray coating, spray printing technology. We are waiting for the questions, but I will first comment on your work. If you about the boron removal, this is a very important topic for all the membranes. The membrane showed here, it seems like it is a nanofiltration membrane, right?
Yep, it is a nanofiltration membrane.
You can achieve 77% boron removal.
Right.
That is really phenomenal. You calculated here, you showed some results, rejection results, and you showed the simulation. The simulation give you a interaction, special interaction of the boron acid to the polymers. But you know, the simulation always, you can adjust the parameters to get whatever you want, to be frank. Right. So I rather take it as a proof or side proof, but I won't put too much emphasis on this data. So would you please elaborate in a bit in some chemistry way, in chemical approach? So what was the real interaction of the boric acid to the polymer you use to be able to increase the boron removal rate for your nanofiltration membrane to such a high value?
Right. Okay. So I believe that complexation of the boric acid towards the hydroxyl group would be one of the more dominant mechanism that we can look into. But however, I also do believe that with the additional layer of APCNC, which eventually we observe that there's a decrease in the water permeability. That would also otherwise tells us that the APCNC layer could have also covered some of the pores that is formed of the polyamide layer itself. So so basically what I postulate from the removal of borons using this nanofiltration membrane would be through two mechanisms. One would be complexation, and the other one would be more of the physical rejection of the boron by minimizing the pore size of the polyamide layer. Yeah.
Okay. That's the logic. Yeah.
Right.
Perhaps your talk is very clear, so there is no not yet the question coming out. I have another question about the spray printing.
Right.
Can you go to the slides where you show how you do this 3D electro? Yeah.
Right.
Yesterday, Professor Rong Wang showed a nozzle to do this work. It was really interesting. You show here the example. Can you make real tight membrane by using this spray coating without disturbing the two aqueous phase and organic phase?
Okay, with regards to the tightness of the membrane, we also face difficulty by controlling it initially. So there would require a lot of pre-treatment of the substrate before we are able to get the two monomeric layers to react on the surface itself. So one strategy would be by using various surfactants on the UF substrate that facilitates our monomeric layers to be tightly sprayed onto the membrane layer itself. So as you can see from this case itself, we only require 2 scans of the printing to be able to achieve 85% of the salt rejection. But of course, we are more optimistic about it when we increase the number of layers of the printing of the TMZ as well as MPD for the fabrication of the reverse osmosis membrane in future also. So this is just a proof of concept in terms of the setup. So we are also working with a NAMIC, which is National Additive Manufacturing Cluster in Singapore, to build a pilot stage fabrication setup for our further proof of value.
Okay, one last question. So when you are coating water phase, and do you also simultaneously spray organic phase, or do you first coat water phase, then organic phase?
No, they are sprayed simultaneously.
Okay.
Right.
Okay. Thank you,
Thank you so
Yang
much.
Ying.
Thank you.
Nice talk. We are ending now this session. I would like to, for the audience, I would like to announce a important information. If you are the speaker of MEMDAS, please check if you have a email which contains the link to log in as a oral speaker. Otherwise, you cannot log in as oral speaker. If you don't have it, please send an email to the conference organizer, which I just posted a message to the WeChat group. If you're not, please send me a message. Thank you. I will see you later. Bye-bye.